All right, so if you've got basic calculus down, you know all about finding the slope of a curve. But what happens when the world isn't just a simple line? Well, today we're jumping beyond that and into the complex, really beautiful math of the real world. And we're going to use Chapter 2 of Marsden and Tromma's classic text as our guide.
I mean, this is the big question, right? This is what vector calculus was built to answer. It is literally the language of physics, of engineering, and so much more. So in this explainer, we're going to build the foundational tools that let us speak that language, all coming from one of the most celebrated textbooks out there.
You know, single variable calculus gave us these incredible tools for functions with just one input. But to describe a landscape like this, where the height depends on both where you are north to south and east to west, well, for that, we're going to need a serious upgrade to our conceptual toolkit.
Okay, so here's the crucial first step. Before we can even think about doing calculus on these new kinds of functions, we first need a way to wrap our minds around them. We've got to be able to see what we're working with.
This right here, this is the big leap. We're going from a function that takes one input x and gives you one output y, and you can draw that as a simple curve. Easy enough. But now we're dealing with functions that take two inputs, x and y, to give you a single output z. And the result? It's not a curve anymore. It's a whole two-dimensional surface living in three-dimensional space with peaks and valleys and all sorts of complex shapes.
So, as Marsden and Tromma's Chapter 2 lays out, we've got two main ways to see this surface. We can try to imagine the whole 3D graph itself, which can be tough, or we can do something a little cleverer. Imagine taking a bunch of horizontal slices through the surface, kind of like floors in a building. Each of those slices creates a simple curve. Then you just project all those curves down onto the flat XY plane, and what do you get? A contour map. If you've ever seen a topographical map for hiking, that is exactly what this is.
And this is a perfect example of how these functions aren't just, abstract math problems. Not at all. They're the language we use to describe real-world stuff, like the temperature at every point in a room, or, as you see right here, the velocity of a fluid at every single point in space.
So now that we can picture these surfaces, let's figure out how we can actually do some calculus on them. Specifically, how in the world do you find the slope of a surface? On a simple curve, that's easy. There's only one slope at any point. But on a surface, it's way more complicated. This is really the core problem of multiple variable differentiation. Think about it. If you're standing on the side of a hill, the slope is totally different if you walk straight up versus walking sideways, right? So which one is v slope? Well, the answer is surprisingly simple and really elegant.
So here's the genius move. We don't try to solve this messy 3D problem all at once. Instead, we pull a brilliant trick. We turn it into a bunch of easy 1D problems we already know how to solve from basic calculus. We just freeze everything except for one single direction and find the slope in that direction alone.
It's kind of like you're trying to analyze a really complex cake. You don't try to understand the whole thing at once. No, you take one clean vertical slice, and that slice reveals a simple 2D curve. And finding its slope, hey, that's a problem we've known how to solve for ages. We just do this for each direction, one slice at a time. Okay, so we've got the info from our individual slices. Now for the really cool part. Let's see how we put it all back together into something way more powerful, something that describes the entire surface at once.
The process itself is pretty simple, but the result is profound. First, we figure out the rate of change just in the x direction. That's one partial derivative. Second, we do the exact same thing for the y direction. And third, this is the key, we package those two numbers not just as a list, but into a powerful new object, a vector.
And this vector has a name. It's called the gradient. Now remember, a vector isn't just a number. It has both a magnitude and a direction. And that is what makes the gradient the absolute master tool here. It doesn't just give us a couple of slopes, it packages them together to point in the single direction of the steepest possible climb. It tells you with total authority which way is up.
And this is exactly why people love this textbook. It's what experts call rigorous, but not overly academic. It doesn't just hand you a tool like the gradient and walk away. It relentlessly shows you why that tool is so unbelievably useful out in the real world.
So let's actually see this amazing tool in action. Why is knowing the direction of steepest ascent so incredibly important anyway?
Well, for one, the gradient is a master tool for optimization. For a hiker standing on a mountainside, that gradient vector points directly up the steepest path. So if your goal is to get to the top as fast as possible, the gradient is literally your map. And the same idea applies everywhere, like in economics when you want to find the best way to maximize profit. This one mathematical idea is, and I am not exaggerating, everywhere. The negative of the gradient tells you which way water will flow down a hill. It describes how heat flows from hot to cold. It even represents the force of gravity, and today, it's the engine behind modern artificial intelligence. Algorithms use something called gradient descent to navigate these huge, complex data landscapes to find the best answers to problems. It's amazing. All right, let's switch gears a bit. We've been looking at static surfaces. Let's talk about dynamic motion, which is another key idea from Chapter 2. See, so far our functions have given us a height, like z equals f of xy. But what if a function gave us a location that changes over time?
This is what Marsden and Tromba call a path. It's a function, usually written c of t, that takes one input, time, and it spits out a vector that tells you a location in space. It is, quite literally, the mathematics of a journey, tracing out the path of a planet or particle moving through space.
And this is where the derivative gets a really cool physical meaning. Just like back in Calc 1 where the derivative gave you the slope of the tangent line, here the derivative of a path function gives you the velocity vector. At any single instant, this vector is tangent to your path, it points in the exact direction you're moving, and its length tells you your instantaneous speed.
So, the crucial point here is that this derivative vector perfectly captures that immediate feeling of motion. Just think about a roller coaster. At the very top of a loop, your velocity vector might be purely horizontal. But a split second later, as you're hurtling toward the bottom of a drop, it's pointing straight down and it's much, much longer, showing just how fast you're going. And just like that, we've really hit the core ideas of differentiation from Chapter 2. We've gone from looking at topographical maps all the way to calculating the velocity of a spacecraft. And we did it all using two fundamental ideas, the partial derivative, which we assemble into the gradient, and the derivative of a path.
So the gradient tells us which way is up, but it doesn't tell us when we've actually reached the top. How do we find the absolute highest and lowest points? Well, that is the next step in our journey, the topic of Chapter 3 and the real secret to optimization in our complex, multidimensional world.